Industrial Revolution 4.0. Innovations in artificial intelligence, cognitive neuromorphic, machine vision, robotics, deep learning, and data analytics are enhancing and improving our quality of life. As intelligent machines learn from their environment and execute self-error correction in order to successfully complete a task and ultimately to optimize productivity.
Developed in our Design R&D Center located in Medellin's Software Valley Technology Park. There will be challenges impacted by the deployment of artificial intelligence worldwide. Equally as important, humans will also benefit from the application of artificial intelligence. It is obviously a paradox. My objective is to illustrate artificial intelligence motor design methodology as it relates to several robotic system applications. The projects were presented in previous videos as applied in unmanned robotic systems, specifically drones and autonomous vehicles. In medical smart pulmonary ventilator for COVID-19 solutions, and robotic arm manipulator industrial applications. These video presentations are available in my video YouTube channel. The motor system paradigm uses MOSFET drivers with 1.2 amperes per channel current capability and can draw up to 3 amperes peak for approximately 20 milliseconds at a time. It also has much lower voltage drops across the motor so to get more torque out of the batteries, and there are built-in flyback diodes supported in this system. The chip also handles all the motors and speed controls over I2C bus. 2 GPIO pins plus a 5-volt and ground are required to drive the multiple motors. The system is completely stackable. 5 address select pins means up to 32 stackable shields. That's 64 steppers or 128 DC motors. And the system also is a pulse width modulator system. The DC motor software constructor takes no arguments. The motor object is typically initialized by assigning the motor object retrieved from the pulse width modulation shield. So create the motor shield object with the default of I2C address. The run function controls the motor state. The parameter can have one of 3 values: the forward, which is rotate in a forward direction; the backward, which rotates in a reverse direction; and release, which stop rotation. Included in the software functions, the void step function controls stepper motor function and controls stepper motor motion. The first parameter specifies how many steps to move. The second parameter specifies the direction, that is forward or backward. The last parameter specifies the step-in style, single, double, interleaved, or micro-step. The STE function is synchronous and does not return until all steps are complete. When complete, the motor remains powered to apply holding torque to maintain position. The void set speed function controls the speed of the stepper motor rotation. The speed is specified in RPM. The one step function is a low-level internal function called by step, but it can also be useful to call its own to implement more advanced functions such as acceleration or coordinating simultaneous movement of multiple stepper motors. The direction and style parameters are the same as for step, but one step steps exactly once. The release function moves all power from the motor. Call this function to reduce power requirements if holding torque is not required to maintain position.
Autonomous robotics, motor methodology and applications. The rotor and stator magnetic field. The rotation is obtained based on the forces between two magnetic fields. One field is located on the rotor, which is the moving part of the motor. The second magnetic field is located on the stator, the body of the motor. Usually one of the two is generated by a permanent magnet, while the other is generated through an electromagnetic solenoid. The magnetic field generation, the relation between electrical energy, which is current, and magnetic field generated by the solenoid coil, is obtained through the formula B equals Ki of pH. The torque, which is the output torque of the electrical motor, depends on the intensity of the rotor and stator magnetic field and on their phase relationship. So the angle theta between the two magnetic fields is named load angle, and the maximum output torque and the maximum efficiency is obtained when the load angle is 90 degrees. So the basic principles of motor design methodology for the unmanned autonomous system is based on the electric motor operation with the following points of interest. At least one of the two magnetic fields is generated by a solenoid carrying a current, and the phase relationship, that is the rotor and stator magnetic field, such as the load angle, must always be greater than 0 degrees in order to keep the motor in motion. That is, negative angles reverse the rotation. The output torque depends on both solenoid currents and the angle and the load angle, and the motor rotation causes a back electromotive force opposing the motion itself.
A pulse width modulation (PWM)
signal is a method for generating an analog signal using a digital source. A pulse width modulation signal consists of two main components. They define its behavior, which is a duty cycle and frequency. The duty cycle describes the amount of time the signal is in a high on state as a percentage of the total time it takes to complete one cycle. The frequency determines how fast the pulse width modulation completes a cycle. So therefore, how fast it switches between how high and low states. It is done by cycling a digital signal off and on at a fast enough rate. With a certain duty cycle, the output will appear to behave like a constant voltage analog signal when providing power to the motor. In this application, the pulse width modulation duty cycle is used to vary the speed of the motor by controlling the motor terminal voltage. The motor voltage and revolutions per minute obtained at different duty cycle rates. As the duty cycle rates increase, more voltage is applied to the motor. This contributes to the stronger magnetic flux inside the armature windings and the increase of RPM. The rotor is composed of a group of coils. The rotor coils are sequentially connected to the motor leads through mechanical switches, brushes. The stator magnetic field is generated by a permanent magnet. The torque applied to the rotor is the highest possible because the load angle theta is about 90 degrees. Forcing a current in the motor causes the rotor to generate a magnetic field.